Need to start a little bit early here. So I sent 4 of you an email this morning to register your iClickers so I can match up everybody. But you need to, even if you register on Canvas, you need to register under your iClicker account, which those emails should have a link. It's like click this link, join link or something, and that should get you kind of registered under your iClicker account. I might prompt you to sign in with your username and password. But I still have 4 of you that need to do that. So I sent you an email this morning that had that link that you can kind of quickly join. If you're not sure, if you're linked up or I'm syncing these grades to Canvas, if you're not seeing yours, send me an email, I can double check. Or even after class, I can look at the list if figure out exactly who. Like I should have gotten an email this morning. So what's due today? Excel assignment. So hopefully you've all started it. But it's due at the end of the day. So you can upload your Excel file and show all of your work. If you want to answer some of the questions, that you're typing out in Word, you should be able to upload multiple files. You don't have to upload it as multiple submissions. You can upload them at the same time. So that's due by the end of the day today. I should try to get those graded pretty early next week. Your individual assignments, I got those graded. One thing that happened, and I'll kind of won't pick on the person, but what I would do if it were me, when you're doing these homeworks, save them not as the name that it downloads as, and save it like add your name to the end of it, right? Because it happens all the time. It's very easy that when I see someone will upload, it's literally the blank file. It's the one they downloaded. It's just for whatever reason, when you're saving it, if you're saving it under the same name and then you re-download it, sometimes you can just kind of erase that file without realizing it. So there would be maybe like kind of change the name once you download it, save it right away with a separate name that maybe it's like Excel homework number 1, and then you put submission, right? So like this is the one I need to submit or something, and then as you're working on it, save it under that new name. So just a little bit of advice there. So before we jump into material today, are there any questions for me? So you've got that Connect assignment that's due at the end of the day on Monday as well, right? So hopefully you've kind of started on that. The last couple questions, I think someone came in yesterday. We figured out it was what, 17 through 20 or 17, 18, 19, and 20 that you couldn't answer all parts of them. And then after today, you should be able to answer every single part on all those 4 last problems. Another thing, there's a couple problems I didn't realize that were on there. They reference something called MAD. So capital M, capital A, capital D. Ignore that. You don't have to put anything in there. It's something that we're not going to use. And so I forgot that they had them in those problems. So when it comes to I think it's 13 and 14, maybe, it has like references this thing called MAD. Don't worry about that. I'll go back in after the due date and kind of give everyone credit for that part of that question. Okay. All right, I think that's all the housekeeping stuff. Anything else before we jump into material today? Okay. So it should be pretty fun today. So we left off talking about percentiles, kind of building this box and whisker plot. I might have alluded to a little bit that, up to this point, we've really been looking at one variable with the exception of a scatter plot, right? So with a scatter plot, we said we were trying to get this idea about the relationship between a variable X and some variable Y. So, a lot of times we might be interested in something like, as people get more education, do we see their income increase, right? Or we're interested in that relationship between income and education. So, as we see X going up, does Y go up? Does Y go down? Or does Y not change at all, right? Is there no relationship between these 2 variables, right? So that might be interesting, right? If, we're thinking about, something like does vitamin D help prevent a certain disease, right? Finding that it doesn't there is interesting, right? And you don't have to necessarily have a relationship for it to be an interesting thing. You can say, oh, this is kind of obsolete. So we're going to come up with 2 measures. The first is the covariance. So you kind of see that word variance in there. It's going to kind of act similar to what the variance did, but it's measuring something a little bit different. And then we'll kind of scale that covariance eventually into what we're going to call a correlation coefficient or just a correlation. You might have probably heard this term used, right? 2 things are correlated. They're moving in the same direction. So we've got population and sample data sets, so we can come up with a covariance for each one. So the setup is going to be, we have 2 variables, X and Y. this is going to be how we find their covariance. So I'm going to write this out and kind of maybe give an idea. Just in a second, we'll look at the data set to see how this would kind of operate, but I'll kind of talk through this, right? So the first thing is, right, we say it's the covariance. So we use this symbol sigma again, right? When we were just looking at, sigma for one variable, that represented our standard deviation. Okay. So the covariance, we're still going to use sigma, but we're going to notate it with two variables representing that it's not a standard deviation. It's instead a covariance between whatever two variables that we use as our subscripts. All right, so this might be something like, you could do, I don't know, income, education, right? Could be our two variables. So we'll kind of analyze this numerator first, maybe get an idea about what's going on here. But having it written out will help me be able to point some things out here. Actually, sorry. Should be kept on. So what we're going to do, right? Hopefully we're getting used to these summation signs a little bit. Once again, I'm not writing it out complete on the board, right? But start from the first, go to the very last observation, and do whatever is to the right of that summation sign for every single observation, and then sum them or add them all up, right? So for every observation we're going to go through, so now I have this data set where we've got all these people's incomes and as well as their years of education. And so we'll look at the very first person, whatever their income was, and subtract whatever the mean income was of that data set. So for people who have above average income, what's going to be true about that difference? It's going to be positive, right? Well, let's say that person has above average education, right? Their value for education is above the average. Well, positive times a positive, we get a positive amount added to that covariance, right? Because that one observation was evidence that when someone is on the right side of the distribution, right? When someone is above average income, this one person was also above the average education, right? So those two variables tended to be on the same side of the average, right? They were evidence that these two things were moving in the same direction. When one of them was higher, so was the other one. Okay, so that would be an observation where they were both above the average. What if we have an observation then where we see someone be below average income? Right, so we would end up with a negative value here. But then we look at their education, let's say it's negative as well. Well, here, negative times negative would be a positive. Well, that makes sense because that observation was also evidence that these two variables tend to be on the same side of the mean, right? When income is lower than the average income, this person's education was lower than the average education. Now, those are just two observations, right? We're going to have to do this for every single observation. And some observations will be evidence that these two variables tend to be on the same side of the mean. But occasionally, we end up with someone like, I don't know, Bill Gates, right? So their income would be way above the average income, so that difference is positive. His education, right, dropped out of college, so it might be that it's less than the average in my data set. Positive times negative, well, yeah, that would be an observation that was evidence that, well, when income is above the average, education tends to be below it. Now, it's just one observation, right? We're going to be doing this for every observation and then adding them all up. So really the covariance is kind of like, and notice we're dividing by n, right? So once again, it's almost like each one of these observations, evidence of the relationship between these two variables is kind of being weighted by 1 over n, right? They're all equally weighted. So the covariance is really kind of an average across all the observations of whether or not these variables tend to be on the same side of the mean or on different sides of the mean. And it's also going to have a value to it, which tells us, the higher that covariance is, the stronger that relationship is between those two variables. The more likely that they'll both end up being on the same side of the mean, right? Or more likely that they'll both end up being on different sides if we end up with a negative covariance. Okay? So we looked at the sample formula. It's going to be exactly the same kind of principles as with the variance, right? It's the same procedure, but instead of dividing by n, we divide by n minus 1. That's the only difference there, right? And we use s because that represents a sample, right? English lettering. Okay. So what does a covariance really mean? If it's positive, it's saying on average, right, these two variables tend to be on the same side of the mean, right? Either both above the mean or both below. If we, add these deviations multiplied by each other for every single observation, and we don't have the negative covariance, well, that tells us that they tend to be on opposite sides of the mean, right? When X is high, Y tends to be low, or vice versa. And then if it's about 0, that tells us that there's no relationship, right? You can kind of imagine if we have a bunch of observations that are adding positive values to that numerator, but then we have a bunch that add negative, they kind of cancel each other out, right? So we could end up with, across every observation, we get basically a 0 up here. The covariance, unlike the variance, can be negative, right? So we're not squaring anything up here. Any questions? I'm going to show you some data here and kind of walk through what it would look like in practice in just a second. But any kind of questions over anything I've said so far? Okay with this? So I had this data set you can download from the CDC, and it's got the height and the weight of a ton of individuals here. So across the 44,000, how can I find the covariance? Well, I've got the mean of each variable, like in Excel. That was very easy for me to calculate. I've got 2 columns of data, equals average for height, equals average of the weight column. I now have my mean height and my mean weight, which is what I need here, right? I'm looking for every observation's deviation from the mean of X times the deviation from the mean of Y. So what I'm going to go through and do, oh, let me see this. I thought I had a slide. Oh, no, I don't need it. Well, I'll walk through. Hold on. Did I open the wrong one? Complete. Well, I'll do it by hand. I thought I had a slide, but I might have accidentally not copied it or deleted it. So what would I do, right? So I'm going to go through for that first person, right? Are they above or below the average height? So 70.4 minus about 64, I'm going to end up with what? About a difference of 6. I'm rounding here. Right? I'm then going to multiply that by however far away from the average Y that person's Y variable was, or their weight. So if you look at their weight, they were actually below the average weight. About what, -8 here. So, you know, if I'm doing this, oops, I put negative. All right. So this one observation, this first person, was evidence that when height is above average, that weight tends to be, that a person's weight tends to be below the average weight. That these two variables are on opposite sides of the mean. Now it's just one observation, right? We kind of know intuitively, like, if I end up calculating this covariance, what's the sign probably going to be between the relationship between height and weight? As people are taller, they probably tend to also weigh more, right? You've got more bones, organs, whatever, right? And so we know that this covariance probably is going to be positive, but from any one observation, that observation could be evidence that there's actually a negative relationship, right? But we go through the rest of these people, that, you know, this person just barely below the average height, right? So I don't know, it's like what? Not even -1, so it's like -0.1, right? But that person was also below the average weight. So when we take that difference, we're going to have a huge negative value there, which is like what, about -50. All right. So here, negative times the negative. Well, that was evidence that these two things tend to be on the same side of the mean. The height and weight tend to be on the same side of the mean. Now we're going to go through do that for every single observation, and then add them all up. Right? Now, I've noticed, like as we work down, like these two people below the average height, they're also below average weight, right? And so those are going to have the exact same kind of situation where we got negative times negative. Those three observations are all evidence that when you're lower, actually, sorry, this one was above. I looked at this at 63.8. That's just 68.3, right? So this person would be above average height, but below average weight. So once again, we'd end up with another negative value being added.
Maybe a stupid question, but when you're dividing by an n, you double the number of operations between two observations.
Yeah, so you have two variables, but we still have 44,000 observations, right? So your n is still going to be 44,000, right? It's a good question. But I also wanted to point out, it's not just about being negative and positive here, right? Some observations might be stronger evidence. These two things tend to be on the same side of the mean or vice versa, or that they tend to be on the opposite side. So for instance, this person is quite a bit above the average height, but their weight was quite a bit below the average, right? So that was a pretty strong evidence that maybe these are on opposite sides of the mean. Well, the next observation, this person was just barely below the average height, right? But their weight was way below the average, right? Well, that means that this one variable was like really close to the mean, but the other one was way below it. So yeah, they're on the same side of the mean, right? They were both below it, but it's not real evidence of a real strong relationship, right? Because one of those variables was really close to the mean, the other one was way far away. So notice, yes, it was evidence that these two things tend to be on the same side of the mean. It adds a positive value in there, but it wasn't very strong evidence. So it won't really counterbalance, right, observations where there was strong evidence of being on opposite sides. Now, obviously, we got 44,000 observations. I'm just using 2 of them here. And so, even though this one doesn't weigh this one out very much, there's probably a bunch of other observations that added in some pretty strong positive values there. So if we end up doing this, you actually end up finding it is about 76, right? So we end up with this positive covariance. Across the 44,000 observations, we do tend to see these two variables be on the same side of the mean. Any question about just kind of the idea of calculating the covariance, how you do this by hand? Now, obviously, I'm not going to make you do this for 44,000 observations, right? 4 or 5 observations, I think, would be very doable. But that's kind of the procedure which we use.
What does it like mean if it's negative?
If it's negative, so once again, you can kind of think about this as the average, right, across every observation of whether these two variables tend to be on the same side of the mean. If it's positive, that means that they're both on the same side of the mean. If it's negative, it means they tend to be on opposite sides. So income education probably doesn't make sense. If we think about something like, let's say I wanted to look at the covariance between hours of Netflix watched and your exam score, right? So during the week, right? Well, there, if someone is watching a higher number of hours of Netflix, means they're not studying, they probably would tend to do worse on the upcoming exam, right? So those two things would tend to be on opposite sides of the mean, right? So we do end up with a negative covariance. That means that as X is higher, Y tends to be lower, right? As X is above the mean, Y tends to be below it. Does that answer?
Yeah.
Any other questions kind of on the procedure? And like kind of like the covariance, or sorry, kind of like the variance, I would probably add in a column where I take, this person's deviation from the mean height times their deviation from the mean weight, whatever that number ends up being, write that number down, right? I create a new column. I would then have this column where I have each deviation times each other. I then add them all up, divide by n if it's a population, n minus 1 if it's a sample. Right? Now there's a built-in formula in Excel. You just think of COV, so you can calculate the covariance. And then you just would select, I'll show you your class. You would select each column, right? It would need you to tell, both columns of data, but it would then calculate the covariance for you. You don't have to do this by hand in Excel. There is this built-in function, okay? But I'll kind of show you, you can imagine you could break it down step by step if you're kind of interested. So we end up with a covariance of 76. Before I go to show you this in Excel, let's think a little bit more about the covariance and how we might need to scale it. Okay. So what does this mean? 76 what, right? Like, I don't know how to, is that strong? Is it not? Well, it's not 0. It's pretty far away from 0, but can covariances be in the thousands? They can. Right? So we're going to notice how the covariance is kind of like the variance. I can't compare across data sets. If my units are different, right, then the covariance, for income and education, I don't know, that's going to be dollar times years. So I'm going to have dollar years. And then height and weight, I'd have inches times pounds. So I've got inch pounds. Like the units don't really make any sense at all, right? So the covariance is a good start, right? The sign of the covariance tells us something. And if I was comparing, let's say I have the covariance for height and weight from a US data set, and then I have covariance for height and weight from, I don't know, Denmark or something, right? So some other country. Well, I can compare those covariances, right? I could say that, you know, if Denmark ends up having a lower covariance than the US between height and weight, that the relationship between height and weight is stronger in the US than Denmark. But I can't compare, say, the relationship between height and weight to the relationship between income and education. Right? So it has its limitations. So what can we do? Right? Well, we just already talked about the units are an issue. So how can I get rid of those units? We can actually scale our covariance by dividing by the standard deviation of each variable, right? So that kind of accounts for the fact that depending on what that variable is, whatever the units are, we're going to see a lot more variance just in terms of the number and income because we're talking about things that are in the thousands, right? Whereas if I'm looking at something like height, I mean, even the range of possible values you can see is much, much smaller. So by dividing by the standard deviation, which represents how much variation there exists in those variables, it essentially is going to scale out, right, the variation that exists in each one. And it's also, I've got inches times pounds divided by inches times pounds, it creates a nice unitless measure. And I can now compare across different types of variables. Right? So the correlation coefficient is much more useful. And you know, there's different notation, but you know, once I've calculated my covariance and my standard deviations, the process is going to be exactly the same. I just take my covariance, divide it by the standard deviation of each variable, and I've got my correlation coefficient. Just that it's population. I'm using population covariances and population standard deviations. It's a sample data. I'm calculating the sample correlation coefficient. I use the sample covariance and the sample standard deviation. So a little bit of an insight as to why this works. I think here I'll allude to it here. Oops. So once we scale it, what we end up with is this really nice measure that's going to range from 1 to -1. Now the sign doesn't change, right? My standard deviations have to be what? We said the variance at the very lowest, the lowest variance we could ever see is 0. So the lowest standard deviation I could ever see is 0. So I know that it's going to have to be a positive value. So where is it? If I'm dividing my covariance by 2 positive values, never going to change the sign, right? If the covariance is negative, correlation coefficient will be negative. Covariance is positive, correlation coefficient will be positive. Because I know that I'm just dividing it by 2 positive numbers, right? So I won't change the sign. So the closer to -1, right? That represents a stronger and stronger negative relationship between two variables, right? That is, x goes up, y tends to be lower. The closer and closer I get to 1, it's evidence that there's a stronger and stronger positive relationship between two variables, right? That as x goes up, y tends to also go up quite a bit. And then as you approach 0, it's kind of getting a weaker and weaker relationship to the point where 0 is no relationship. So why does this work? So we think about what we're doing. We're just taking this covariance and dividing by the standard deviation of each one. So here was my covariance equation. I'll use the population just to kind of go through this example. And then I'm going to divide that covariance by each standard deviation. What was the standard deviation equation? Looks like that. We have the square root of the variance. And then multiply that by over here for my y variable. Here will be its standard deviation. Okay. Now, I'm not going to walk through the mathematical proof. You could Google it if you're interested. Stop by sometime. I'll go through it with you. It's kind of interesting. But you can kind of see what's happening here. Right? I'll do some incorrect math, but you can at least see kind of where it's coming. If I've got the square root of n times the square root of n, that's just going to be, well, the square root of something times the square root of the same thing is actually just, so yeah, if I was like square root of 2 times the square root of 2, it's 2, right? So I'm going to end up with, you can kind of see just an n here. Well, if I'm dividing this by n and dividing this by n, it's going to end up canceling. Like I said, I can walk through step by step, pull it out, but we can show that it's going to cancel. And then this is where it doesn't exactly cancel out, but you can kind of see if I'm taking the square root, but each one of these deviations is getting squared, it's almost like this is going to cancel. It's not, that's not a law of mathematics. That isn't exactly what's happening, but you can kind of see that, right? Square root of things that you're squaring, this is kind of going to cancel. And then notice you're kind of seeing I've got the sum of the deviations for the x variable, sum of the deviations for the x variable, sum of the deviations from the y variable, deviations from the y variable. It's not going to cancel so that this is always 1 because adding up the product is different than adding up this times, or sorry, multiplying the sum of these time, by the sum of these. It's a little bit different mathematically, but you can kind of see where it's not going to perfectly cancel, but it's going to scale everything, right? So that I'm going to get things that are only between 1 and -1, depending on the sign of my covariance. There's that. You don't have to understand that, but you can kind of see it's got the similar components, and we are essentially just scaling that covariance so that it has no units, and that we're accounting for the variation that just exists in the original variables x and y that we were looking at. So, in practice, if I'm doing this, I had that CDC data, we had the covariance, I've got the standard deviation of each one of those variables. It's as simple as taking 76 divided by 3.9 times 43. Now, obviously, order of operations becomes important here. You need to make sure you're dividing 76 by whatever this product is. Right? But pretty easy. So we get about 0.45. Right? So is that a strong relationship? Is it not? Well, I mean, 1 is the strongest, 0 is no relationship, so somewhere in the middle, right? Usually we think about strong correlations being something that's above 0.7, right? So 0.7, 0.8, that would be a pretty strong correlation. So this is definitely not weak, but it's not the strongest, right? I mean, if I told you, to predict somebody's weight, if I told you their height, well, I mean, for any one person, you could be off quite a bit, right? We know that there is a positive relationship, but there's a lot of other factors that go into what someone's weight is as well, right? And so, positive relationship, but not the strongest, not the weakest. Okay. So, if we think about a scattered plot, right? This isn't perfectly how you can, this isn't a perfect estimation, but one way to think about it is, if I was to draw a line that best fit this data, if it's sloping upward, that's going to be a positive correlation coefficient or a positive covariance. If I had scatter plot data that looked like this, where if I was going to draw a line that best fit it, it was sloping downward, well, that would be situations where I'm going to get a negative correlation coefficient or a negative covariance, because as x goes up, y tends to be lower. Excuse me. So we're really just able to capture that, though, with one measure, right? One statistic, that correlation coefficient. Yeah.
So what's Fx and Sy again?
So this is just,
How'd you get those numbers? Are those standard?
yeah, so I had the data.
Okay, so those are both the standard deviation of both the height and the weight.
Yep, so you can think about x and y here was that CDC data where we had height and weight. So from that data set, we calculate the covariance, talk through that, walk through that process. Standard deviations, we're going to talk about how to calculate those. I basically would have in Excel, a column for x, column for y. I could just take the standard deviation. Yeah, sorry. I'm
You're
pulling
fine.
those out of thin air, right? Yeah. So what if I had something like this, right? So we can start to think about different correlation coefficients. So here I've got children, and I believe my x and y variable here. This was something about, there was some test. So I think this y variable was their performance on some test. It wasn't scored out of 100. And then the x variable was, I remember right, like the days of school or average days of school missed. I can't, like, let me think of a better one. So I know this is going to be positive. So children, I think, oh, I know what this was. This was, so this APGAR score, and I think not mother's age. This would have been length of pregnancy or something. Right. So where you had like, the longer of pregnancy, the healthier child ended up being. So it's some measure of, the longer pregnancy, you tend to see that there's higher kind of health score, right, for the baby that's being born. So all we would do here, first of all, which one can we rule out right away? What did I say about the correlation coefficient? It has to be between 1 and -1. So B doesn't make any sense. What else can I rule out here? C, right? Because the sign of my correlation coefficient has to be the same as the sign of my covariance, right? Because when I'm scaling it by just dividing by standard deviations, those are always positive values. So I know that if the covariance is positive, which I have up here, right, that sample covariance between these two variables, I know the correlation coefficient has to be positive. But from there, just take 330 divided by 8.13. Oops. Thought I had it up there, so I'll write it up on the board. So we've got what? 330 divided by 8.13 times 48.51 ends up being 0.84. I mean, it shouldn't be tough. It should be like an easy one if I ask you a question like this in the exam. So let's hopefully see how everyone else or how everyone's kind of understanding this. So we give you a little bit of time, work with the people, talk with people, you know, around you. Well, if I can get this to work. So here I've got two different variables, and there's a reason why I'm using them. I'll show you something, probably watch a video here at the end of class that'll be related to this. I think brings up an interesting point. Oh, this is going to work. I might have to restart this. Okay. This is annoying. All right. Now it's working. Okay. So let's say I had these two variables. Call the one some measure of like attractiveness or beauty. So that's variable X, and then the other one's variable Y, which is wave. So this kind of goes along with this video I'll show you, but kind of trying to estimate the relationship between is there a premium kind of paid to, I guess, better looking, but this is, there will be an actual good point to this, trust me. So we've got the covariance between those two variables, which is relatively low, 0.18, right? But the variance that existed in those variables, or the standard deviations, were also relatively small, right? So if I wanted the correlation coefficient, which of the following would that be, right? So you have a little bit of time to work on that. You got the covariance, you got the standard deviation. Hopefully this should be a pretty easy one to do. And then we'll talk about it here in just a second. Did I forget my one? Oh. All right. We haven't gotten an answer in. Take your best guess here. 13 of us. 14. There we go. All right. I'm going to close this out. So this should be as simple as what? Taking my covariance of 0.18 and doing what? Divided by my two standard deviations, right? It shouldn't be too crazy. I think if I could, there we go. All right, if I do this math out, I should get it pretty close to 0, right? That there is a positive relationship between these two things, but it's pretty much no relationship, right? Really, really close to 0. Any questions on that? Any troubles? Everybody got it right? Which one could I rule out right away? 1.2. I know it has to be between 1 and -1. Also, if I'm looking at a positive covariance, I know that I also have to have a positive correlation coefficient, right? So I really could have had a 50-50 shot without even doing the work here. Okay. So we'll watch this here in a second, but I want to kind of bring up, now that we've got these correlation coefficients. So let's say height and weight, I think that was 0.84. and we just found this one was what? So beauty wage was 0.06. So what could I say about the relationship? Actually, this was not 0.84, was it? I think it was 0.45. So what can I say about the relationship between height and weight relative to that of kind of this measure of beauty and wage? There's a much stronger relationship between these two variables than there is between these two. And then what if I had, let's say I'll make this one up. So let's say I've got Netflix and the exam scores. So let's say this is negative 0.29. What would I be able to say about the relationship between Netflix, hours of Netflix watching exam scores relative to these two? Well, first of all, it's a negative relationship, right? So as X goes up, Y tends to go down, right? So it's a little bit different than these positive relationships. But if I said which of these has the strong, if I had to order them in terms of just the strength of the relationship, doesn't matter like which direction. Well, the relationship between hours of Netflix watching exam scores isn't quite as strong as height and weight, but it's a stronger relationship than would exist between kind of this beauty measure and wages, right? So even if they don't have the same sign, I could say that this is a stronger relationship than the relationship between these two variables, right? Because it's closer to 1 than this one is closer to -1. Does that make sense? So even if they've got different signs, I can compare the strength of the relationships there. All right, so this is actually something that someone's done. We'll watch it, like I said, like a 5-minute video we'll kind of end class on. But it does get at like a pretty important thing. So this guy, he doesn't describe it as well in the video, but he did this really interesting study where they had otherwise identical resumes, and then they created these LinkedIn profiles using different photos, right? So ahead of time, they showed, a couple hundred people these photos and had them rank every single person's attractiveness. So they then put them into percentiles, right? So they figured out like each of these photos is in what percentile of beauty, right? To whatever these, people that they were surveying was. Once they had that measure, they put those photos up as a LinkedIn profile, had the exact same resumes, applied to the exact same jobs. And what they found was that if you were in a higher percentile, right, that photo was in a higher percentile, you tended to get a higher number. And I noticed this upward sloping line. That correlation coefficient was positive between the percentile that the photo was in and the number of interview requests that person got. And you can kind of see here for men, it's slightly increasing. But what they found is that for women, it has huge impact, which is obviously like not a good thing, right? Because it shouldn't be playing into the role of whether or not these people are getting interviews, right? These correlation coefficients like allow us to like identify, right, some things that might be an issue, right, or something that we might want to address, right? And this is just kind of a good example. The Economist ended up on Comedy Central, and so we will watch that here for about 10 minutes. So I want to introduce the next topic though that we'll start covering next week. Okay, so that's kind of if we're following along with have an ebook or something. That was chapter 3. Right? That was like looking at all these different statistics that we could calculate. So the next thing we're going to do is move on to probability. Okay? So I don't know. I have got a couple questions here. Like, what are the odds that something had, right? A new investment becomes profitable. What are the chances sales decrease if I do something? What is the likelihood a new assembly method will increase production, right? All these are really just ways of saying the same thing, right? Chances, odds, likelihood. We're talking about what's the probability that something happens, right? We know that, like, we can talk about this in terms of percentages, right? But what we're going to do is really, percentages are just an easier way for us to talk generally. When we're actually calculating these, we'll be dealing with what we'll call, probabilities, right? So 100% chance of something happening is a probability of 1, right? And then 0% chance, probability is 0. So we know probabilities will be somewhere in between 0 and 1, right? There's either a 0% chance something happens or a 100% chance, right? We're somewhere in between. The probability is just a percentage scaled to a decimal, right? So move the decimal 2 places. So the setup is going to be, we're going to run some experiment, right? So we think about experiments here. All an experiment means is that it's something that we don't know the outcome of, right? So it doesn't have to be like a sign. Don't think about like hard sciences, like the Bunsen burners and stuff. Like here, it could be as simple as I'm flipping a coin. I don't know what the outcome is going to be until I flip the coin. I might know what the possible outcomes could be, right? Heads or tails, but I don't know the outcome of the coin flip until I actually flip it. So we're going to be thinking about, these experiments. We want to be running them in the exact same way. So with a coin, it's pretty easy. Like, let's say, I can't call it heads and tails. Like, let's just say there's two sides of the coin. I don't know what's on them. Maybe it's like, I don't know, a picture of a tiger on one side and a picture of a lion on the other. But I don't know what those pictures are, right? If I'm got the coin, here, I flip it, it lands, I can see what's on one side. I flip it again, as I flip it more and more, I'm eventually going to get both sides of the coin. I now know all the possible outcomes. And I know that if I flipped it, a million times, about what percent would it come up? If you want to think about it, heads, what percent would it come up tails? I flip it like a million times, I should end up with about 50%, right? Where a probability of getting heads or a probability of getting tails would be about 0.5. But, I don't know that going into it necessarily, right? Maybe it's a weighted coin. Well, if it's a weighted coin, then if I flip it a million times, maybe I see that 60% of the time it lands on heads and only 40% it lands on tails. But I don't necessarily know that going into the experiment, right? If you just hand me a coin, I can't tell if it's weighted or not. If I flip it enough times, I'll be able to understand whether or not it's a fair coin, 50%, or something else, right? Non-fair coin. Always, another way to think about this is, let's assume I've never seen a card deck in my life. I don't know what cards are, right? You hand me a deck and I start pulling a card out at random. Okay, so first I pull out, oh, there's a 9, right? And of hearts. So I know that's one of the possible outcomes. Put the card back in, shuffle it, pull another card. Maybe I see now, oh, there's a king of spades, right? So over time, right, if I run this experiment drawing one card out of the deck at a time, I'll eventually realize what all the possible outcomes are, right? But going into it, I may not know that. Right? I don't know what the outcomes are. Okay? So experimental outcomes are going to be what we record or what we see from running this experiment. So for example, if I only pull 5 cards out of the deck, my experimental outcome space is actually going to be smaller than the actual outcomes I could see, right? Like I'm just recording what I see after I run this experiment. Now, if I run this experiment enough times, I'm going to see every possible outcome, right? But in a small, limited number of running this experiment, I may not. So our sample space, we can then think about as kind of this thing that we're recording, right? Experimental outcomes, everything that actually exists, we might not even be able to know that. Like if I've never seen a deck of cards, my experimental outcomes is saying, ace through king. I don't know that maybe though. And if I only draw 5 cards, maybe I only have 5 of them in my sample space, right? If I've only run this experiment 5 times, I'm only going to see maybe 5 different types of cards. And then we'll start talking about things like an event. This is just going to be a smaller number of outcomes than we see from running the experiment. So the event is going to be like a subset of our sample space. So maybe if you think about, let's say I roll a dice, roll a die 3 times, I see a 2, 4, and 6. That's my sample space. An event might be, I'm interested, okay, what's the probability I see just a 2? Well, that was just one outcome from my sample space. And because I only rolled this die 3 times, my sample space is actually smaller than the possible experimental outcomes I could see, which is 1 through 6. If I'm using a regular die, like a Dungeons and Dragons or something like 20. So here's a visual, right? You've got all these experimental outcomes. You run this experiment a number of times. You've got whatever you see from those experiments in your sample space, and then you might be interested in just a small subset of those, which would be kind of the event you're interested in. So if we think about experimental outcomes here, the possible outcomes we could see if I flip a coin would be what? Heads, tails. That's pretty easy. If I roll a die, once again, I'll use this example a lot because it's just really easy. I think everyone can envision a 6-sided die. You can see 1 through 6. If I'm choosing cards from a deck and I don't care about suit, ace through king, I can think about if I'm playing a football game. I think here I've got think about this as a playoff game. Maybe I either see just win or lose. Maybe a regular season soccer game, I see win, lose, or tie, right? So anything can be an experiment, right? As long as we have an unknown outcome, right? We don't know what the outcome is going to be. We know what it could be, but we don't know which of these it's going to be, right? Once the game is played, I don't know if the team's going to win or lose. If I'm going to die, I don't know what number I'm going to see. I may know the possible numbers I could see, but until I run that experiment, I don't know. Any questions on this? So I'm just kind of getting this out of the way. Let's get us set up for next week. We'll really do a deeper dive into probabilities. I'll show you some Excel stuff. We'll do contingency tables. So I put that smart book for the next chapter up there. That's really going to be over probability. That's what we're going to be tackling next week. Okay. And we'll kind of end today. I think this is meant to be funny. Hopefully, I don't know, you appreciate the humor, but if not, at least you get 5 minutes off class, right? We'll see. Hope this isn't crazy loud. And then I'll have a comment or two at the end of it. So the end of it's not anything that's that fun, so on it there. But no, so this guy, I actually met him once. He's actually really smart. But he was the guy that did that study where they sent out those identical resumes. And like he mentioned, they've done it in different things too, like loan applications, where they're using like a profile picture that they have kind of ranked in terms of the percent of attractiveness. So it's pretty interesting research because, you know, shouldn't be playing a role, but we see it kind of through our statistics, our correlation coefficients that we can calculate. There actually is a relationship there. Yeah, a little bit of hopefully brevity to end the class. So make sure you upload to Canvas your Excel homework by the end of the day today. Other than that, have a fun, safe weekend, and I will see you guys on Monday.